okay, take a look at what students are asking. This is one that I thought about asking, but I'm not sure I have a chance to talk to him and tell him, because really kind of playing the devil's advocate. So I'm not sure what I'm going to ask. Number one, students will be here that day. And I think that actually happened tonight. So let's look at then it doesn't do enough good for anything. Sorry, it's really lazy. Why not? Because you see, that's what the Narola's book is about. Trying to look, when I mean,
Sawadika. Good afternoon, Chairman of the Thai Advisory Board for the second and final event series, Bridges, Dialogues Towards the Culture of Peace. First Vice President of Kasikon Bank, Chairman of International Peace Foundation, President of Southeast Asia University, and all distinguished guests. Southeast Asia University, in collaboration with the International Peace Foundation, are honored to host the event series, Bridges, Dialogues Towards the Culture of Peace for the second time. In this particular series, it is a special privilege to have the keynote speaker from the United States of America to deliver his speech on science and its relevance to international cooperation and a peaceful society. At this moment, I'd like to call upon Chairman of the Thai Advisory Board for the second and final event series, Bridges, Dialogues Towards the Culture of Peace, for the opening address. Ladies and gentlemen, please welcome Privy Councillor General Surayut Chulanon.
Ladies and gentlemen, it's my great pleasure to be here this afternoon as Chairman of the Advisory Board of the Foundation. I would like to present a short speech as a contribution to the decade for a culture of peace and nonviolence, which is initiated and promoted by the United Nations General Assembly. Thailand has been chosen as the host country for the event series, Bridges, Dialogues Towards a Culture of Peace, initiated by the International Peace Foundation, a non-political independent foundation under the common patronage of the 21st Nobel Peace Prize laureates based in Vienna. Between November 2003 and April 2004, already more than 100 events took place, with 10 Nobel laureates, as well as with other keynote speakers and artists, including the Reverend Jesse Jackson, Professor Marcia Hedy, and Ismail Ivo, Dr. Karan Singh, the Honorable Garrett Evans, Dame Anita Lodick, Jacob Juan Brooksville, and Jesse Norman, who all came to Thailand without any fee or honorarium to promote the kingdom as a center for dialogue and international understanding. Her Royal Highness Princess Mahachakri Surinthorn graciously presided over several events, which in total reached an audience of 30,000 participants, including different target groups, thanks to a variety of partners ranging from major universities and ministries to the Royal Thai Army, NGOs, businesses, media, and the diplomatic corps, which hosted the events in cooperation with the International Peace Foundation. After the completion of the first series of events and a 6-month intermission, the second and final series of bridges with additional 150 events is being hosted in Bangkok, Chonburi, Chiang Mai, Chiang Rai, Kanchanaburi, Khon Kaen, and Nakhon Ratchasima between December 2004 and April 2005. For this second and final event series, 17 Nobel laureates for peace, physics, chemistry, medicine, and economics have confirmed their participation, as well as other keynote speakers, including former UN Secretary General Boutros Ghali and former UN Weapons Inspector Hans Blix. The pluralistic program of Bridges highlights the International Peace Foundation's intercultural and transdisciplinary approach towards peace. The foundation doesn't take sides, but acts as a mediator by creating an independent platform for dialogue where representatives of science, politics, economy, culture, religion, the media, and youth can meet, share their viewpoints, listen to each other, and find mutual ways of understanding and cooperation. As peace cannot be achieved instantly, but is a process which needs time, Bridges has not been organized as a single conference, but as an ongoing series of events in which Nobel laureates and international decision makers build bridges with Thai leaders in all parts of society and with the general public. Many of these Nobel laureates and keynote speakers have already vowed to come back to Thailand on a regular basis to build long-term relationship with major Thai institutions and with Thai nation itself. Thank you.
Thank you very much, Privy Councillor General Surayut Juranon. And next is the first Vice President of Kasikorn Bank. Ladies and gentlemen, please welcome Mrs. Janjira Buranatwe.
President of Southeast Asian University, Associate Professor Narong Sinsawat, Chairman of the Thai Advisory Board of Directors of the International Peace Foundation, Private Councillor General Jurayut Suranon, and distinguished guests. In celebration of humanity without borders and admirations of Thailand as a peaceful country, Kasikorn Bank is proud to sponsor speeches by 17 Nobel laureates in 5 months, from December 2004 to April 2005. Each Nobel laureate will deliver his or her keynote addresses at various universities all over the country as part of the International Peace Foundation's Richest Dialogue Towards the Culture of Peace project. On behalf of Kasikorn Bank, I'm honored to present Professor Baruch S. Blumberg, Nobel Laureate for Medicine. Thank you.
Thank you very much, Mrs. Chandra Buranawe. May I now call upon our distinguished President. Ladies and gentlemen, please welcome Associate Professor Dr. Narong Sinsawat.
His Excellency, the Private Councillor General Jurayut Suranon, Professor Baruch Blumberg from Fox Chest Cancer Center, Philadelphia, Kuntantari Buranawe, the first Vice President of Kasikorn Thai Bank, and Dr. Pridi Kasemsak, who is the former Rector of Thammasat University. On behalf of Southeast Asia University, faculty staff, and students of Southeast Asia University, we welcome all of you to our campus. In the history of mankind, we benefit a lot from the contribution of scientists. Nowadays, we have aeroplane, motor car, we see the movie, television, we enjoy the cool of the air conditioner, to name a few. A most important contribution of scientists for mankind is in the field of medical science. We live longer and could cope with sickness much better from the advance of medical science. In the history of mankind, many discoveries have helped to save billions of lives. Many illnesses can be overcome. For example, the vaccines for smallpox and the hepatitis vaccines, which in Thailand we call low virus TAP. In the history of mankind, we have many great scientists whose discoveries have helped mankind to live a better life and to understand and control nature better. Examples of the great men are Isaac Newton, Thomas Edison, Madame Curie, to name a few. They were great men and women of science. Today, it is a great honor for our country, Thailand, for our university, Southeast Asia University, and all of us here, to get to see in person a great scientist of modern time, Professor Baruch Blumberg, whose discoveries of the vaccines for the hepatitis type B has saved millions of lives, including people of Thailand. Today is the second time that the International Peace Foundation of Thailand, with His Excellency General Surayut Churanon as the chairman of the advisory board, and Kun Uwe Morowitz as the chairman of the Thai branch of the International Peace Foundation, has helped to bring famous keynote speaker to our university. Today, the topic of Professor Blumberg will be science and its relevance to international cooperation and a peaceful society. We cannot live happily in this world based on only material well-being. We have to live in peace. And today we can hear how science is relevant to the building of the culture of peace. Therefore, pay a good attention to the speaker. It is a speech we should remember as long as we live. Thank you very much.
Thank you very much, President Narong. Now, I am proud to introduce you our keynote speaker today. Not only is he a distinguished scientist at Fox Chase Cancer Center in Philadelphia, but he is also professor of medicine and anthropology at the University of Pennsylvania. He was awarded the Nobel Prize for Medicine for discoveries regarding new mechanisms for the origin and dissemination of infectious diseases. In addition, he invented an hepatitis B vaccine that has saved millions of lives by the prevention of acute and chronic hepatitis and primary cancer of liver. It is the first cancer vaccine in general use. In 1999, he was appointed the director of the National Aeronautics and Space Administration Astrobiology Institute that is dedicated to the study of the origin, distribution, and future of life on Earth and in the universe. Ladies and gentlemen, please give a warm welcome to Professor Dr. Baruch S. Blumberg.
Privy Councillor, President, Rector, Vice President, Chairman of the Board, students and faculty of Southeast Asia University, and guests. I'm very honored to have been selected to come and speak to you, and thank the introducer for the very kind comments. Science is one of the most international of human activities. Natural science deals with phenomena that prevail in many locations on Earth, independent of their political boundaries. The image on the screen was taken from the Apollo 17 spaceship, the moon, on its way to the moon, shortly after it took off from Kennedy Space Center on December 7th, 1972. It is one of the most commonly produced images in the world, and many of you have probably seen this in the past. It shows the Earth, beautiful blue, with white clouds, deep sea, land masses, without political boundaries, without any demarcations, that would prevent passage from one place to the other. It's a metaphor for the one-worldness that we live in, and also shows the world altogether and emphasizes the importance that science be studied in very many parts of the world in order to understand the general phenomena that prevail everywhere. Science, international cooperation thrives best in a peaceful world where there's unlimited scientist-to-scientist access and unrestricted travel. Now, the universality of scientific understanding and of human interest goes even beyond the confines of the Earth. This image, the Hubble Ultra Deep Field, was taken during multiple orbits of the Hubble Space Telescope that was focused on a region of the sky that was dark to ordinary telescopes or to human vision. Because of the multiple exposures, a great deal of light was accumulated, and images that were very faint could be seen in this picture. Now, some of these objects are very early galaxies that date back to within a few hundred million years of the time of the Big Bang, within a billion years of the Big Bang. So in a sense, we're looking down a column deep into time and space. And these strange multicolored or colored images there, the light emitted from them that we're now perceiving on this film many billions of years ago. So this is a deep image into space. So far, the deepest image that's been taken. Now, one of the realizations in science in the past few decades is that scientific laws, the principles that govern science, are general and cosmic in their extent. There's a general mathematics, that is the mathematics that pertains on Earth, also pertains deep in space. The universe are about the same proportions, and different cosmic bodies differ. And as far as one can tell, the same chemistry that applies on Earth applies elsewhere in the universe. There appears to be a general geology. The same principles that govern understanding of geological formations on Earth can be used to understand what is seen, observed, measured on Mars or on the Moon, elsewhere where it's been possible to closely examine geological features. What we don't know is whether there's a general biology, whether the kind of life, or for that matter, any kind of life, exists in places in the universe other than Earth. So we only know of life on this Earth here. A new discipline has developed to try to bring together major academic disciplines, major scientific interests to understand these problems. Is there life beyond our own home planet, Earth, or are we alone in the universe? How did life begin and evolve on Earth? Did life come here from elsewhere? These are all questions. And what's the future of life on Earth and elsewhere in the cosmos? Now, to solve these fundamental problems of interest to humans altogether, independent of their nationality, requires international cooperation. And in science, international collaboration, interaction between scientists in different parts of the world is the rule rather than the exception. Now, at a personal level, scientists share much in common. They are usually educated from the same textbooks. They very often have the same teachers, go to the same institutions. And science is based on the belief in an ordered nature. That's understandable. Science can't operate unless you recognize there's some order to it, there's some structure, that phenomena are predictable. Now this understanding should, and often does, leads to a reasonable approach to problems, or at least those that lend themselves to the scientific process. There's an expectation of rational behavior that is often carried from the scientist's professional world to other aspects of his or her life, and that's an attitude that's conducive to civil behavior between people in other nations. Now in this talk I plan to discuss examples of scientific programs that transcend national boundaries, examples from history, from the physical, geographic, space sciences, and from medical science. It's remarkable the degree of collaboration between scientists. Even during the Cold War, Western and Soviet area scientists were in professional and social contact that often prevailed even when their home countries were in dangerous confrontation. And I'm going to use, as I said, some examples from history, earth and space science, and biological science. Now I'd like to talk about a historic example. Alexander Humboldt was a German scientist whose dates were 1769 to 1959, and he died 1859, so he lived to be about 90. Was one of the most famous men of his age, and one of the most noted scientists during his action-packed life. He wanted to try to understand the world altogether. He wanted to know about geography, physical sciences, biology, chemistry, ethnology, linguistics, economics, and all their aspects. Now, to find this kind of unity in nature, he realized that he had to be an explorer, to study different regions of the world, looking at the same phenomenon, to compare natural processes under very different conditions, and look for the unities that connected them. He was born in Germany, spent much of his life in France, traveled extensively in the then Spanish colonies in South America and North America. He visited many places, briefly came to the United States, where he visited Philadelphia. This is an illustration of a building that was standing when he came to the city, and a replica of it still stands. It's the library of the American Philosophical Society in Philadelphia, of which he was elected a member. He visited, in his late in life, he did an extensive tour of Asian Russia, and during the period when he was the chamberlain and diplomat in the court of Frederick William King of Prussia, he did various, many foreign trips on behalf of the king. Now, there are several concepts that he examined, which are examples of how, of this interconnectedness of natural phenomena. This illustration, and I don't expect you to read the fine print there, is an attempt to put in a graphic the variation of plants with altitude. So this is kind of a cartoon of the mountains in the Andes, showing the species that lived at different altitudes, ranging from tropical species at the base all the way up to temperate climate, then subtropical, subarctic, and Arctic botany in a vertical dimension. And we also extended these observations horizontally and looked for differences in different parts of the world. And again, this idea of trying to look for a unity by examining similar phenomenon in different geographic locations. Now, he invented this concept of the isotherm, which is a metaphor, you might say, for this interconnectedness of phenomena. The more or less horizontal lines represent regions on the world with the same temperature. The vertical lines indicate different latitudes. And again, these kinds of observations to find temperatures in different parts of the world and their exact location required a great deal of international cooperation. And this line showed the connections between these points. He was also very interested in geomagnetism. That is the measurement of the direction and intensity of the geomagnetic force that surrounds our Earth and in fact protects us from solar and cosmic radiation. We wouldn't survive without a magnetic field around us. And it's generated because there's a fluid center to the Earth and because of the movement of tectonic plates. So he made many observations when during his trip to South America, using a horizontal magnet so that he could see the dip of the direction of the magnetic lines, and he could also estimate intensity. But then he wanted to extend these measurements to other parts of the world. When he was in St. Petersburg in 1829, he recommended to the Russian authorities that they set up measurement stations throughout the huge extent of the Russian Empire, and quite soon there were measurement stations all the way from St. Petersburg in the western part of the country to Beijing and to Alaska. In 1834, Gauss, a prominent scientist interested in geomagnetism, set up an international cooperative effort that facilitated simultaneous multi-station magnetic observations extending across Europe all the way from Ireland to Germany. Now, in 1836, Humboldt communicated with a friend of his, the Duke of Sussex, who was the president of the Royal Society in London, and he proposed that the British establish a series of magnetic measuring stations throughout their empire. And in fairly short order that was done, and there were stations in Canada and St. Helena Island, in the mid-Atlantic, South Atlantic, in South Africa, in Jamaica, and elsewhere. And these were manned by the Royal Engineers. Regular measurements were taken. These measurements were extended even further when some years afterward there was a naval expedition to the Antarctic under Sir James Ross, during which time he found the magnetic South Pole. These geomagnetic network and this idea of international cooperation was the antecedent of the international polar projects of 1882 to 1883 and 1932 to 1933, and also of the International Geophysical Year of 1957 to 1958, a major international scientific collaboration soon after the Second World War. Now, perhaps the most remarkable of international agreements based on science is the Antarctic Treaty. Now, I'm going to read this statement. There are a few places on Earth where there has never been war, where the environment is fully protected and where scientific research has priority. But the whole of the Antarctic continent is like this. A land which the Antarctic Treaty Parties call a natural reserve devoted to peace and to science. And I want to show you the provisions of the Antarctic Treaty signed in 1961. The demilitarization of the Antarctic, although military personnel are allowed to participate in scientific research. The establishment of a nuclear-free zone and a test zone with the absence of nuclear waste. The dedication of the use of the territory only for peaceful purposes. International scientific cooperation and the setting aside of any sovereignty disputes. Although the treaty did not negate the existing claims. And this illustration shows the initial founders, the 12 nations that were doing research at the 1961 when this treaty was signed, and then the other signatories who have since joined them. So, to my knowledge, this international treaty, the idea of peace, of cooperation, that was established 40 years ago or more, is still as operative and working effectively. There's plenty of ongoing research in the Antarctic, very often centered in research stations funded and staffed for the most part by the nationals of the country that funded the research station. But at any of these research stations at any given time, you're likely to find scientists of different nationality cooperating in research that is of interest, a particular interest to them. So this again is, to my mind, an outstanding example. This is the Dry Valley area, shows this bottom picture of the Dry Valley area, which has been of considerable interest in studying astrobiology, the study of the origin of life, and the question of why life exists elsewhere, because it's thought that the environment of these dry valleys has similarities to the environments on early Earth, and therefore early Mars. So that gives some possibility of experiencing, studying these areas that we are interested in studying, whether there's life on Mars, for example. I just want to point out that Thailand has a space agency. It was promulgated by a royal decree in 2000, and there was a great interest in geoinformatics obtained from the Earth orbiting satellites that has very good imaging capability, and this is one of the agencies that Thai interests in space is challenged. Now there are other international treaties that in a way were modeled on the Antarctic Treaty. One of the most important of these is the Treaty on Principles Governing the Activities of States in the Exploration and Use of Outer Space, including the Moon and other celestial bodies, and also known as the United Nations Space Treaty of 1967. So this was set up just about the time that serious exploration beyond our own Earth into space was beginning. And I've reproduced the preamble to the treaty, again pointing out the notion that space should be reserved for peaceful pursuits, that it should not be militarized, that it should be used for joint international space research. And I'll just show you that in the other provisions of that are set forward in this preamble. So again, this is a treaty which is currently in existence, and again, as far as I can tell, is still being followed. Now, there were other treaties that followed on this. There was an agreement governing the activities of states on the moon and other celestial bodies, and this was opened for signature in 1979. Now, as a matter of fact, many countries have decided not to sign this moon treaty, although many of its provisions are covered in the space treaty which I just showed you. There's some concern because there's an interest in commercial exploitation of the moon. As odd as it may seem, there is much thinking, planning on the possibility of mining the helium-3, which is quite common on the moon and very rare on Earth, which may have some use in fusion, in production of fusion energy, and actually is currently used in certain forms of medical imaging. Now, there are other, this again is the continuing provisions of the Moon Treaty. Now, emerging from these, from this International Space Treaty are other provisions. The Committee on Space Research of the International Council of Science, which is a non-governmental body, they have a planetary protection policy that was written in 2002. This deals with the issue of the possibility of cross-contamination. That is, that when we send spaceships to Mars or to Mercury or to Jupiter, to Saturn, to try to avoid any possible contamination of those planets, and also as objects are brought back to space to Earth, to prevent possible contamination of Earth by these objects. Now, kilos of moon rocks have been brought back to Earth. They're distributed widely around the world. They're curated into various locations. There's a plan for return missions to Mars, that is, robotic missions that will assemble and collect geological specimens on Mars and return them robotically to Earth. And there's also very long-range plans on human missions to Mars, which would include scientists who would be able to return to Earth. So there's a great deal of thought given to this notion of planetary protection. Now, the space effort is huge in size, in engineering vision, in science possibilities, in its cost. It's extremely expensive to do space exploration, and the requirement for people of exceptional talent and skills in order to do this. And this requires international cooperation. Now, the International Space Station, which is currently in orbit, is an example of the international character. There are some 15 or so nations that are involved in the International Space Station. As I'm sure you all know, there was the tragic loss of the shuttle Columbia several years ago, and in 2003, and that has had a very bad, devastating effect on the project. Following the loss of the Columbia, the space shuttle fleet was grounded in order to incorporate the new safety features into it, and the expectation is that there'll be a return to flight this year, perhaps in a few months. But during this period, when there wasn't shuttle access to the space station, this was provided by the transport capabilities of the Russian space authority, and they have supplied the Soyuz spaceship, which can transport people back and forth, and also the Progress freight ship, which can bring needed supplies to the space station, allow it to be continue to maintain it, and to continue with some scientific experiments on board, and also to bring back waste material from the space station. So this is I have to call it a remarkable example of international cooperation in achieving space exploration. Now, the Mars, the current interest, major interest now is several of the planets in our solar system. There's currently 3 orbiters circling Mars. 2 of them are NASA orbiters, funded mostly by the United States, and one, the Mars Express, is a European Space Agency orbiter. In addition, there are 2 rovers on the ground now on opposite sides of Mars. There was a third lander, the Beagle 2, which unfortunately was lost during descent. Now, the missions are quite international. Scientists from many nations are involved with the missions that are being undertaken by the rovers on the ground. The Mars Express, which has just recently taken some very amazing high resolution images of the surface of Mars, showing what appears to be a frozen lake with ice flows, recently created ice flows in it, which raises the possibility that there was liquid frozen water fairly recently. And that image was just taken within the last few weeks. Now, I've shown you here a few slides. This is Olympus Mons on Mars. It is the biggest volcano in the solar system. This was a Viking image taken some years ago, and superimposed on it were data from the Mars Orbiter laser altimeter, which gave remarkably accurate altimetry data from Mars, actually better than we have from Earth. This is a diagram of one of the 2 rovers, their Spirit and Opportunity, showing this rather complex device, which locomotes on these 6 wheels. It has at the close to ground level navigational cameras, which allows the rover to do a certain amount of decision making in traversing the territory. There's 2 cameras mounted on that stalk that sits up vertically, and there are a variety of about 6 other instruments for making spectrometric and other measurements of on Mars. Now, these rovers were designed with a 90-day life expectancy. They've now been operating for well over a year, way beyond expectation. Really quite a remarkable achievement. This is one of the landing sites taken from one of the orbiters, where the Meridiani Planum. This is the other landing site, the Gustav crater. The ellipse in the center shows the expected landing region. And this is a image, a mosaic image, a composite image of the day-to-day progress towards the Bonneville crater of one of the rovers. And this is a close-up photograph of the ground, just taken from these navigational cameras, or this one from the cameras on the stalk, to give some nature of what the surface of Mars is like with these oxidized iron dust over much of it. And this is a long-range picture from the cameras on the stalk, looking back to where the lander was in the top central part of the picture, and the tire tracks as the rover proceeded from its landing site, and hills in the background. Now, another mission with a great deal of international cooperation is the Cassini mission. And that was launched about 7 years ago, and recently arrived at Saturn. This is an artist's image. This isn't a photograph, but an artist's image of the Cassini immediately after it approached Saturn, and it was about to be, rockets were to be fired to insert it into the orbit of Saturn. A very successful maneuver, by the way. It's one of these things you have to get it exactly right, or else the orbiter could have been lost. And this is the signal sent over miles and miles of space. Now, attached to the Cassini orbiter was the Huygens lander. Now, the Huygens lander was a European Space Agency project. The Cassini orbit was NASA and the Italian Space Agency. This is, again, an artist's image of the Huygens lander descending. Its fall was interrupted by a series of parachutes that were deployed at different times. The moon Titan is the only moon in the solar system that has a substantial atmosphere, and as a consequence you could use parachutes to slow down the fall. The atmosphere is toxic, it's mostly methane. The Huygens descent was again successful, very successful, and somewhat unexpectedly it actually survived on the surface of Titan for several hours and was able to take images of the immediate landing site. It showed these frozen methane rocks and frozen lake surfaces, and also kind of a semi-frozen, slushy surface made up of this frozen or partially frozen methane gas. So this again is an artist's image of what it was like. And these are some images taken of Titan by the Cassini orbiter using radar techniques, radar images, again showing these river-like structures, what appears to be a crater, conceivably, but could be a volcano as well, and other regular features on Titan, which much of this data has now been retrieved, and it'll take years for the scientists to fully assimilate and analyze this data. And I just wanted to, again, come back to this theme that when we try to study origin of life on Earth, one looks for features on contemporary Earth that have resemblance to early Earth and to early Mars. Mars and Earth were much more similar soon after they were formed than they currently are. So one of the interests is in the study of impact craters, that is where meteorites have hit the Earth. This is the barrage of meteor crater in Arizona, and that impact was about 40,000 years ago, and this is about 1 kilometer across, so it was a relatively small meteorite. There are about 120 known terrestrial impact craters that are known on Earth. It's only since 1920s or even later that people appreciated that these were due to meteoritic impacts. And this is another crater in the Canadian Arctic on Devon Island. It's the Houghton crater. It's about 20 kilometers in diameter and formed about 23 million years ago. Again, it's in a frozen Arctic region, it has similarities to sites on Mars. Now, it's not exactly the same. There's an atmosphere and all that. That Mars has a very different, very little atmospheric pressure. There's also an interest in studying geothermal sites on Earth because it's thought that life may have originated in geothermal sites. And there are many geothermal sites that are of interest. This is one that's been studied quite extensively. It's the Grand Prismatic Spring in Yellowstone National Park in Wyoming and Montana, a site of multiple and very interesting geothermal locations. This is a black smoke or a geothermal site under the sea that harbors a very interesting flora and fauna, including a microfauna and flora. Now, I'd like to step down from space and talk about scientific projects in medical science, and in particular about the research that my colleagues and I were engaged in. And again, this had a very international character to it. It required travel to many different parts of the world. In each of the places, we worked with local colleagues, local scientists, and medical people. And the results of the research are applicable all over the world. This is a diagram. Actually, when I was preparing my slides, I found this sitting on a shelf somewhere. I prepared it about 20 years ago, I guess. And it shows some of the field sites, some of the places where we did collections of medical material in the period from 1957, when the work was started, until the early 1970s. So you can see there's an extensive international coverage by ourselves and our colleagues who were working in this field. Now, the hepatitis B virus was discovered not as a consequence of a direct search for it, but because of our interest in human variation and how this variation, both inherited as genetic variation and variation due to the impacts of the environment, how that relates. We were interested in seeing how that variation relates to susceptibility to disease. Everyone is different from everyone else. If you can recall seeing two people who looked exactly alike. The world's a very heterogeneous place. And even identical twins who share a common genome actually aren't exactly alike, because there have been phenotypic alterations of the expressions of the genes. So we recognized that there were these multiple differences, genetic and environmental, and the notion was that this would be related to the way people responded to disease agents like viruses or other agents. And this eventually led to the discovery of the hepatitis B virus, because there had been a strikingly different response to, in this case, two different individuals after they were infected with the hepatitis B virus. One of the people infected developed an antibody against the surface antigen of the virus, and the other person, when infected, retained the virus. His cells produced large quantities of the virus, and the antibody discovered in one person can be used to identify the antigen found in another. Now, this is an electron micrograph, and it shows the several particles that are produced by the virus when it infects the liver cells of the host, of the person it's infected. The larger particles, the one that's shown in the diagram at the bottom, and is shown as having 42 nanometers, in diameter. That's the whole virus. It contains the surface antigen, core antigen, other antigens, and the DNA of the viruses inside this particle. In addition to the whole virus particle, there are smaller particles, the ones that are marked as 22 nanometers and are shown in the diagram below. They're circular, and also some of them are elongated. Now these particles contain only the surface antigen of the hepatitis B virus. And my colleagues and I were able to invent a vaccine, produce a vaccine, which was actually made from the blood of people who carriers of the hepatitis B virus. The surface antigen particles, those smaller particles, were separated from the whole virus particles by centrifugation, column separation, and other techniques. And then the infectious whole virus discarded, and the surface antigen particles, after appropriate treatment, were the vaccine. So millions of doses of this vaccine were produced. They were tested. The vaccine was found to be highly effective. Its protection was about 90+%, which is very high for a vaccine. In the initial studies, and I think it's fair to say in most of the subsequent studies, it did not seem to have serious side effects, fortunately, and it began to be used in the 1980s, and vaccination programs began then. Soon afterwards, techniques for producing the vaccine by recombinant methods were devised. And the gene that produces this surface antigen, the one that is on the surface of the whole virus and constitutes those small particles, that gene was incorporated into yeast and other cells, and vast quantities of the vaccine could be produced. Now, as a consequence, there have been large vaccination programs around the world. All right, just to say a few words about hepatitis, there are various kinds of hepatitis viruses. There's hepatitis A, which is transmitted by fecal oral route, that is by eating or drinking contaminated water or foodstuffs. Hepatitis B, which is what we're talking about now, that's usually transmitted by transfer of blood or body fluids from one person to the next. Hepatitis, and I'll come back to that in a moment. Then there's hepatitis C, which is, again, a totally different virus than hepatitis A or B. It's transmitted in manners similar to hepatitis B, which I'll discuss briefly, but it's less infectious than hepatitis B. There's hepatitis D, which is a very strange virus that is only transmitted along with hepatitis B or to people who are already infected with hepatitis B. And then there's hepatitis E, which occurs in large epidemics in Southeast Asia, fairly common, and in South Asia and India. There are other viruses as well, but those are the major pathological ones. Now, getting back to hepatitis B, the methods of transmission include transmission from mothers who are infected with the virus to their children. And it also is transmitted readily between sibs, between brothers and sisters. If one child is a carrier hepatitis B virus, there's quite a high likelihood that it'll be transmitted to another brother or sister. And it's also transmitted, it's a sexually transmitted disease, one of the most common sexually transmitted disease. So the transmission of hepatitis B virus is related to human behaviors, human functions that are essential to the perpetuation of the human race. So as long as humans perpetuate themselves, the virus had a capability of being transmitted. Fortunately, that can be interrupted by the use of the vaccine, which is usually given in some cases to a child immediately after it's born, or others during the first few months of life. Now, hepatitis, I'll now focus on the pathological consequences of hepatitis B. is very widespread. About 1/3 of the world's population has been infected with hepatitis B virus, so 2 billion people. Now, most of the people who are infected, this is true for most infectious agents, they don't develop any disease, but they develop an antibody against, they develop a protection against it. However, there are some estimated to be about 375 million people around the world who are currently infected with hepatitis B virus. Compare that to AIDS, the AIDS virus, HIV virus, about 40 or 50 million people in the world, so it's multiple times there. And its distribution is different in different parts of the world. It's very common in East Asia, Southeast Asia, and in Africa, and in the Amazon basin in South America. Strangely, it's also very common among the Inuits, Eskimos, in North America and Greenland. That's a relatively small number of individuals altogether. So, and then there are other places where there's an intermediate frequency in South Asia and India and parts of Southern Europe and Eastern Europe and elsewhere in South America. And again, it's very common in Papua New Guinea and Guadalcanal, and it's very common here in Thailand. So the distribution is uneven around the world. The people who are chronically infected with hepatitis B virus, that is among these 375 million or so, have a much greater likelihood of developing primary cancer of the liver and chronic liver disease. Chronic liver disease is a major killer in the areas where hepatitis B virus is very common. Primary cancer of the liver is mostly caused by hepatitis B virus infection and also by hepatitis C virus infection. Primary cancer of the liver is the third most common cause of death from cancer in males in the world, and the 7th most common cause of death from cancer in females worldwide. It's a very difficult cancer to treat, unfortunately. But the vaccination programs have made a big impact on this, on the prevalence of and incidence of these diseases. Now, beginning in the mid-1980s, vaccination programs were started in different countries. Some of the early ones were in Asia and in South Italy, in Italy altogether. And a evaluation in 2003, the WHO noted that about 80% of the 192 countries that are members of the WHO had universal childhood vaccination programs. So that means millions, tens of millions of people are vaccinated and have been vaccinated. Now, there are about 90 members that have high prevalences of the hepatitis B virus, and about 70% of them have these vaccination programs. So the vaccination program is widespread. Now, the effects have been very positive. For example, in Thailand, there were studies done on the prevalence of hepatitis B virus prior to the initiation of the vaccination programs, and in regions of the country, the prevalence was about 15%. That's about 15% of the population were carriers of the virus. Now, measurements have been made in the population after the vaccination programs that were in place for several years. And the prevalence has dropped to about 2%, a very large drop. Now, it's interesting that the prevalence has dropped both in the people who got the vaccine, but also the people who did not get the vaccine. So presumably the decrease in prevalence in the younger age group has also had an effect on the continuation of the infection in older people who are not vaccinated. Very strange phenomenon. And this has been observed in many parts of the world. So there's good reason to hope that this disease can be very greatly decreased, that primary cancer of the liver, currently a great terrible killer, will decrease considerably. There's already evidence that that's the case from studies that were done in Taiwan and in South Korea. So altogether, we can look forward to a very wholesome outcome of the use of this vaccine. Well, what I've tried to do in this, I'm afraid, too long talk, is give illustrations both from history, from space science, geological science, and from medical science about how scientists collaborate, cooperate in order to achieve their, to increase their understanding of nature and to have applications that are valuable in preservation of health, prevention of disease. And I like to think that these examples, and there are many others, of international cooperation is a kind of model that hopefully could be followed in other of human activities. Thank you very much.
So no matter what centuries we are in, and no matter where we live in the world, international cooperation is the rule leading to peaceful society. As sharing interesting and new information leads to remarkable discoveries. So thank you very much, Professor Blumberg, for your contribution. At this juncture, the floor is open for questions. If you have any questions, please step forward to one of the microphones provided in the aisles. Okay, we have the first one, Professor Vincent.
I very much appreciate about your research because it's very useful for mankind. About your research, which is relating to the recovery of HPV and the invention of the vaccine to prevent infection, I would like to ask you some questions. What is the difference of gene distributions in the populations who living in the different environmental, for example, in Southeast Asia region, especially in Thailand? Thank you.
There are undoubtedly many reasons why these differences exist. Part of it is due to genetic differences between people that make them more susceptible to persistent infection once they have been initially infected by the hepatitis B virus. There are also environmental factors. For example, certain toxins that are present in contaminated foodstuffs increases the probability of primary cancer of the liver in people who are already infected with the hepatitis B virus. It's possible that increased iron levels in certain periods of life, increased iron levels in the host, may increase the possibility of becoming a carrier once infected. It's again a surmise, but probably the multiple infection, the possibility that is, if there's increased probability of exposure to the virus, that this may also increase the possibility. But in a way, there may have been some some advantages to having these susceptibility genes in the past. And once the chronic infection is established in the population, since it's transmitted from infected mothers to their children, it's very hard to interrupt that transmission route. And since it's transmitted by the sexually transmitted, it's a sexually transmitted disease. Once established, it's perpetuated unless these programs, unless the vaccination programs are used. So I think it's fair to say there are multiple causes for these differences from place to place.
Okay, so the possible causes can be genetic differences between people and polluted environment, right?
Yes.
Okay. Okay, next question.
Good afternoon, Professor Blumberg. My name is Prof. I'm in Faculty of Arts and Sciences. According to your speech, science has brought mankind many good things, but it has also brought us some bad things, like the atomic bomb and other dangerous weapons. How can we, as non-scientists, help to make sure that scientific and technological advances are used in good ways rather in bad ways?
The discoveries very often lead to both good and bad effects. It's one of the ironies of life that's the case. I think that the general answer to that is that one would hope that there's a kind of thoughtful, humane, and rational consideration of these problems by society in general, by people who govern and lead a country, that they can use the better outcomes of research rather than the bad ones. My experience, I think the experience in the last many decades that I've been doing science, is that scientists don't have any bigger impact on the use of their inventions than other people do. So it's you can perhaps understand the issues better if you worked on them and done the actual research. But I don't get the sense that we have any more of an impact on governmental and political decisions than anybody else does. So it's up to the rest of you, it's up to all of us to try to use things well, reasonably.
Thank you.
Okay, right. It depends on us ourselves. We will consider whatever should be good for us, and we take it.
Yes.
Okay. And next question, please. Okay, Ajahn Narek.
Good afternoon, sir. So the topic seemed to be difficult for me since I had studied this subject when I was a high school student. So coming to see again that it is true that almost all kinds of diseases in the world needs, the science to help to cure the disease. But exactly I want to go beyond science, beyond what I mean here. So I just read a book named Creating Sustainable World Peace, International Award-winning essay, written by Thai writer. So her name is Associate Professor Dr. Sukita Onkong, who won the international award, so maybe from UNESCO or from some organization, I forgot. So, sir, I have two questions. The first one is that I want to quote the passage from some very interesting person, one from Einstein. If I can't remember well, this year was signified as Einstein year in Germany. So Einstein said that Albert Einstein lamented that atomic bomb had changed everything on Earth except human mind. So I come to the book I mentioned recently. So Dr. Sukita said in her book, page number 18, she said that our progress in science and technology has not helped us bring peace. and harmony to ourselves and to our world. The more advanced we are in the national aspects of our lives, the more advanced we are in the material aspects of our lives, the more we are at wars with ourselves and each other, and the more crimes and social ills there are in our human societies. The question is, do you believe that science without religions, I mean Buddhism, Christianity, maybe Islam and those, etc., can solve the problems, the disputes between society and society, countries and country, as we see in Iraq and any corner in the world? This is the first question. Do you believe that science without religion can solve the problems and bring peace to our world? So the second question is that, quite interesting, I saw from your presentation recently, I just learned that, is Mars worth living for human beings? The second question is that, is Mars worth living for human beings? Thank you, sir.
Thank you. Science is a scientific process is a very effective method for solving many problems, but it can't be used for, as a matter of fact, most problems. The scientific process works very well in the areas where it's applicable, but those are quite limited, and it doesn't lend itself to resolving many issues that are very important to humans, such as religious thought, spirituality, taste, emotions, love, hate. Science doesn't deal very well with those. So I don't think it does. It very often can't be applied. So the notion that you can use science to solve everything is I think the point that you made is quite appropriate. So everybody else has got to work very hard to solve those other problems. Is it worth leaving Earth? I don't think that's a current issue. That's not what's being considered. What the current investigations of Mars are to learn more about our environment. Humans have an enormous curiosity. They want to know about the world about them. In the last few decades, because of engineering and technological advances, we're able to examine places that we've never seen before. We not only never seen or measured, we never could because you couldn't get up there to see them. So now there's this great sort of unknown out there, and humans have this need to investigate the unknown, to find out about the natural world around us. And that's the immediate goal. Now there is also an interest in humans going to Mars, and humans in the first instance probably going to Moon. The United States has, the Space Agency has set that as an interest, something they would want to do. And this is the Chinese government during last year, has stated they have a program to go to the Moon and possibly Mars. And other countries have the European Space Agency have also shown an interest in that. But so the initial, if that happens, it will be for the establishment of, in effect, research stations on the Moon and possibly Mars. But there are a great deal of obstacles to be overcome before human travel of that kind is feasible. For example, it's very difficult to protect humans in space from solar radiation, which is deadly, and from cosmic radiation that descends into our solar system. But I have to say it's a non-issue right now, because leaving Earth to go to Mars is to the extent that it's being done now, it's part of this interest that scientists, researchers, and matter of fact humanity have in the world that's around us.
Thank you, sir.
Okay, thank you. Now, we would like to have a few more questions.
Good afternoon, Professor Blumberg. My name is Chalalai from Faculty of Arts and Science. And my question is, how can we prevent the most powerful nations in the world from withdrawing from international agreements like the UN Space Treaty of 1967 and using their nuclear weapons in space?
Well, I don't, my understanding is that people, that nations are still adhering to that treaty. And the way that you can prevent nations from taking actions you don't like is by, when it's possible, voting on these issues. So, we live in democratic countries, and the methods of changing the effects of those countries is dependent on citizens' decisions about who's going to lead them and who's going to make these changes.
Thank you very much.
So,
Do we have more questions?
Good afternoon, Professor Blumberg. I'm Tanyala from the Faculty of Arts and Science. And my question is, would you please explain exactly what astrobiology is and how it might benefit mankind? Thank you.
the definition or the statement that's often used to describe astrobiology is the study of the origin, distribution, evolution, and future of life on Earth and in the universe. So this is a basic study of basic scientific questions that has to do about how life started here. We know there's life here because we're all here. There's other living material. And it's a fundamental scientific question of how it began. And the second part of the program is to determine whether there's life existing in places other than Earth. And at the moment, the major interest is in Mars, because that's within reach with the rovers there, their orbiters. And there's some other locations in the solar system, such as the moon Europa, the moon of Jupiter, which is also of great interest because it appears to have a liquid water interior. So that's the definition. And again, there are other factors that come into it. For example, we have to understand what the characteristics of life are, how you describe life. Because if you're looking for life on Mars, how would you know you found it? You have to have some idea of what to look for. And if you're looking at the beginning of life on Earth, let's say, how would you know you found the beginning? So we have to have some understanding about what life is. Again, a very fundamental scientific question, and a question of interest in other areas as well. The question of how it would apply, there's a kind of general answer to that. And one is that the experience of science, that is, when you're doing basic science, there's an expectation, you might even say a faith, that just trying to understand nature will in time lead to very useful applications. For example, the interest in organisms that live under extreme conditions. As I mentioned this, in astrobiology, people study organisms that live in geothermal sites and deep under the sea, in high and low acidity locations and extreme locations. That's identified organisms that have very interesting characteristics that are used in molecular biology. For example, the whole basis of molecular biology is based on the use of enzymes that were found in an archaea, an organism that lives in a geothermal site. And the space, so first of all, you want to do this in order to understand nature, understand the world around you. That's the goal of basic science. There's a kind of expectation and a faith that in time it will have applications that you can't even predict when you start the research, except you know there's going to be something, but you don't know what it is. That's why science is exploration, it's discovery, it's full of surprises, it's full of mysteries. Mysteries that in time you solve, and you also create new mysteries. So it's part of this search that goes on. The space program has resulted in many contributions. For example, well, having satellites, or satellite transmission of information, telecommunications, that's a direct result of the space programs. Various imaging techniques that are used in medicine that depend on programs that were developed in space. And a whole variety of devices that we take for everyday use now were a consequence of the space program. But at the beginning, it wasn't at all clear that they would have applications. Thank you.
In Thai astrobiology, we say Darasat Chiva Vitya. And we need to have expectation of faith to understand the nature of discoveries. Right? Okay, any question? Okay, Ajahn Dylan.
Good afternoon, Professor.
Afternoon.
Do you believe that science today is receiving bad press? In particular, what one reads sensational stories in the press about various things?
I'd say it has bad press and good press. There's a kind of interest in sensationalizing things. Newspaper readers and therefore newspaper writers like to read something out of the ordinary, something very often something that's negative. But also there's quite good coverage of the press. I'm reading the papers here in Thailand, and I thought there are many thoughtful and informative and well-written articles that I've seen since I've been here, particularly on developmental issues, that is development of techniques for use in rural and the poorer areas in the country. So I think on balance, it's not bad, the coverage of press.
Okay. Any other questions? Please don't feel hesitate to come to the microphone. We still have time. Okay, Ajahn Dale.
Good afternoon, Professor Blumberg. I'm going to be playing the devil's advocate, and I hope you don't mind. But during the last 100 years, there have been huge successes in science and technology. These successes were accomplished during some of the most serious and bloodiest conflicts in the history of mankind, specifically 2 world wars, the Korean conflict, Vietnam, not to mention the overall Cold War, and the current age of international terrorism. So why is peace so crucial to scientific cooperation?
Well, it's, I guess you could say the world is ironic. That is, it works differently than you think it should. And I think the experience is that very often the demands of war are extreme. That is, you have to do a lot of difficult things. And society is prepared to put a lot more money and effort into research that leads to what they need to be needed for their protection or to win a war or something. So as a consequence, they have major efforts. Some of the efforts to develop munitions and arms during the wars have been the biggest expenses on science, technology, and research that have ever been. But generally speaking, the useful applications, that is the non-war applications of these initial discoveries, come during peacetime, when they can be applied to other uses. So I think your provocation is appropriate. That is that war stimulates a great deal of insight and drives people to extremes, not just in science, but I mean, people do things during wartime that they would have never demanded of during peacetime, and they do exceptional things. And but the full exploitation, full use, very often comes when we do have peace, interaction, and people that work together on scientific questions rather than hiding, concealing the data.
Thank you.
Thank you.
Okay, any more questions? Shall this be last question? I don't think we have anyone who would like to deliver any question. Okay, we have come to the end of the event, and I'd like to take this opportunity to call upon our distinguished president to present a token of appreciation to the keynote speaker, and followed by the closing address.
With your permission, Professor Blumberg, I would like to say in Thai language to my students, so that it's like a make a conclusion remark. ก็นักศึกษาก็คงฟังนะฮะว่าที่ประการแรกเลยเนี่ยนะที่ท่านอาจารย์ท่าน Professor Blumberg เนี่ยได้พูดถึงเนี่ยท่านก็พยายามจะพูดว่าการผลงานของนักวิทยาศาสตร์เนี่ยนะมันจะมีจำนวนมากเลยที่เขาร่วมมือกันนะฮะอย่างเช่นที่เขาพูดถึงเรื่องอาจารย์ชาวเยอรมันนะฮะซึ่งเมื่อศตวรรษที่19เนี่ยเขาได้ไปท่องเที่ยวไปทั่วโลกเพื่อที่จะค้นหาเรื่องแม่เหล็กโลกเนี่ยนะฮะแล้วก็เขาต้องใช้เรื่องความร้อนนะฮะความร้อนในที่ต่างๆของโลกเนี่ยซึ่งมีอุณหภูมิที่เท่ากันเนี่ยนะฮะบนเส้นรุ้งเดียวกันเนี่ยเขาก็ไปศึกษาเพราะฉะนั้นคนเดียวทำไม่ได้ต้องใช้ในหลายประเทศนะเพราะฉะนั้นโปรเฟสเซอร์ชาวเยอรมันท่านนั้นเนี่ยก็นักวิจัยชาวเยอรมันท่านนั้นก็ต้องไปอเมริกาต้องไปอเมริกาใต้ต้องไปที่รัสเซียเนี่ยนะคือว่าการศึกษาหรือว่า Space Station นะก็คือกระสวยอวกาศไม่ใช่มันเป็นสถานีอวกาศที่มันอยู่ข้างนอกโลกเนี่ยนะฮะซึ่งกว้างเท่ากับกว้างยาวกว่าสนามฟุตบอลอย่างเงี้ยนะฮะ ก็มีนักวิทยาศาสตร์ทั้ง15 ประเทศร่วมมือกันนะเพราะฉะนั้นลักษณะของหรือว่าเมื่อสมัยที่สหรัฐอเมริกากับรัสเซียเนี่ยกำลังมีเขาเรียกว่าการต่อสู้กันในโคลด์วอร์หรือสงครามเย็นเนี่ยนะนักวิทยาศาสตร์ของทั้งสองฝ่ายเนี่ยเขาก็ยังร่วมมือกันนะเพราะการเป็นนักวิทยาศาสตร์เนี่ยมันจะมีความร่วมมือกันในการคิดค้นของเขานะซึ่งถ้าเราปรับไปเมื่ออาจารย์ท่านเจ้าชายอัลเฟรดที่มาคราวที่แล้วนะท่านจะพูดไปอีกแบบหนึ่งนะเจ้าชายอัลเฟรดเมื่อมาพูดเนี่ยท่านได้พูดถึงว่ามีนักศึกษาถามว่าประเทศเนี่ยทำดีหรือไม่ดีเนี่ยนะดูตรงไหนเจ้าชายอัลเฟรดเนี่ยมีนักศึกษาถามอย่างนั้นเจ้าชายอัลเฟรดบอกว่าการที่บอกว่าการกระทำของประเทศหนึ่งดีหรือไม่ดีเนี่ยจะต้องดูทั้งเป้าหมายและวิธีการเป้าหมายและวิธีการถ้าเป้าหมายดีนะครับเช่นอยากเขาเป็นประเทศประชาธิปไตยแต่ไปฆ่าคนเขาซะตั้งเยอะเนี่ยเพื่อที่จะให้เขายอมเป็นประชาธิปไตยเนี่ยวิธีการก็อาจจะไม่ถูกนะนั่นก็เป็นลักษณะมุมมองหนึ่งนะที่เราได้ประโยชน์ไปนะแต่วันนี้ที่ท่านอาจารย์บัมเบิร์กท่านมาพูดเนี่ยท่านก็พูดไปอีกแบบหนึ่งนะสิ่งที่สำคัญอันหนึ่งที่ท่านมองเห็นเนี่ยท่านก็บอกว่านักวิทยาศาสตร์เนี่ยเขามีจุดหมายเพื่อการค้นพบเท่านั้นเองนะเขามีเพื่อการค้นพบนะแต่ว่าเมื่อค้นพบแล้วเนี่ยคนจะไปใช้เนี่ยมันเป็นเรื่องของการนำไปใช้นะเพราะฉะนั้น discovery คือการค้นพบเนี่ยนักวิทยาศาสตร์เนี่ยเขาเป็นช่างคิดนะคิดแล้วเขามีความสุขของเขาเมื่อคุณเอาไปใช้เนี่ยมันเป็นเรื่องของ public นะที่นักศึกษาถามว่าเราจะป้องกันยังไงนะที่ไม่ให้เอาผลงานทางวิทยาศาสตร์ไปใช้ในทางที่เลวเนี่ยนะอันนี้เขาบอกว่านักวิทยาศาสตร์เขาป้องกันไม่ได้นะนักวิทยาศาสตร์เขาป้องกันไม่ได้เพราะว่านักวิทยาศาสตร์เนี่ยเขาคิดค้นขึ้นมาแล้วเราก็ไปใช้เหมือนกับคนเขาคิดประดิษฐ์ปืนอย่างเงี้ยนะฮะถ้าประดิษฐ์ปืนเนี่ยถ้าเราไปยิงผู้ร้ายมันก็เป็นการใช้ที่ดีถ้าเอาไปยิงคนดีไปปล้นธนาคารอะไรเนี่ยมันก็ใช้ที่ไม่ดีเพราะฉะนั้นมันเป็นเรื่องของ public คือสังคมเนี่ยจะต้องเป็นตัวจักรสำคัญนะที่จะเอาผลงานของนักวิทยาศาสตร์มาใช้ในทางที่ดีหรือไม่ดีนะเพราะฉะนั้นเพราะฉะนั้นเราให้เข้าใจคำนี้ว่า science เนี่ยนะ science เนี่ยนะวิทยาศาสตร์เนี่ยจุดประสงค์ของมันคือ understanding คือความเข้าใจไม่ใช่ application คือการนำไปใช้เพราะนั้นนั่นก็คือเทคโนโลยี science เนี่ยเขาค้นพบเฉยๆนะเทคโนโลยีก็คือไป apply ใช้เพราะฉะนั้นการไป apply ใช้เนี่ยมันจะต้องขึ้นอยู่กับผู้ไปใช้นะขึ้นอยู่กับ public เพราะฉะนั้นที่มีคนถามว่าเรามีนักศึกษาคนหนึ่งถามว่าถ้าผู้นำประเทศเนี่ยไปถอนตัวออกจากสนธิสัญญาร่วมมือกันในอวกาศเนี่ยนะแล้วจะป้องกันยังไงนะท่านก็ตอบว่านักวิทยาศาสตร์ป้องกันไม่ได้นะมันเป็นเรื่องของประชาชนของประเทศแต่ละประเทศเนี่ยจะต้องป้องกันเองนะถ้าผู้นำที่ดีเราก็ต้องเลือกผู้นำที่ดีนะถ้าเราเลือกผู้นำไม่ดีก็ไปทำสิ่งที่ไม่ดีนะเพราะฉะนั้นก็หมายความว่านะไม่ใช่นักวิทยาศาสตร์เนี่ยเป็นผู้รับผิดอย่างนั้นนะครับต้องเป็นประชาชนทั่วไปเนี่ยต้องเป็นผู้รับผิดชอบในสิ่งที่เขาประดิษฐ์คิดค้นขึ้นมาเนี่ยอีกอย่างหนึ่งเนี่ยผมอยากจะชี้เห็นก็คือว่าเมื่อคืนเนี่ยผมไปทานข้าวกับท่านนะกับท่านเนี่ยแล้วก็มีท่านจันเดลแล้วก็มีท่านอาจารย์มีคุณยูเว่นะแล้วก็มีสตาฟของคุณยูเว่3-4 คนเนี่ยนะนี่ทั้งหมดเรามี6 คนเนี่ยไปทานข้าวเนี่ยผมสังเกตที่โต๊ะเนี่ยนะอาหารเนี่ยนะท่านจะถามท่านจะไม่ได้คุยเรื่องของท่านเท่าไหร่เลยท่านจะถามว่าอาจารย์ณรงค์ทำอะไรคนนี้ทำอะไรถามแต่ละคนเนี่ยนะท่านถามแล้วถามลึกซึ้งนะฮะไม่ใช่ถามไปอย่างเดลเนี่ยอาจารย์เดลเนี่ยเราไม่เคยรู้เลยว่าอาจารย์เดลเนี่ยเป็นนักมวยมาก่อนอาจารย์เดลที่เป็นนักมวยนะฮะแล้วเป็นนักมวยไทยเลยนักมวยที่เก่งเคยน็อกแต่ก็โดนน็อกเหมือนกันนะท่านถามอาจารย์เดลว่าต่อยกี่ปีได้เงินหรือเปล่าเป็นอะไรคือแล้วก็ถามว่านักมวยไทยเนี่ยต่อยประมาณใช้เวลาประมาณกี่ปีเมื่อไหร่เลิกแล้วไปทำอะไรคือท่านสนใจทุกอย่างหมดเลยนะอันเนี้ยมันเหมือนกับที่ผมเคยอ่านว่าขงจื้อเนี่ยใครถามว่าขงจื้อใครคืออาจารย์ของท่านขงจื้อบอกว่าคนทุกคนที่เดินกับฉันเนี่ยเป็นอาจารย์ฉันทั้งนั้น คือท่านจะฟังคนนะอันนี้นักศึกษาต้องจำไว้คนที่ฉลาดเนี่ยคนที่ใฝ่หาความรู้เนี่ยฟังเยอะและอ่านเยอะถ้าคุยโม้เยอะมันจะไม่เคยรู้เพราะฉะนั้นที่ดีเนี่ยต้องจำตัวอย่างท่านเนี่ยเป็นตัวอย่างจำไว้เลยว่าท่านเก่งขนาดนี้นะแต่ท่านก็หาความรู้ตลอดเวลานะท่านหาความรู้ตลอดเวลาท่านถามหมดเลยแม้แต่ถามว่าดอนเมืองเนี่ยมันไปทางทิศไหนอะไรคือท่านสนใจทุกอย่างหมดนะแล้วก็มาสังเกตมานิดเดียวว่าท่านสังเกตท่านพักโรงแรมดุสิตเนี่ยท่านออกไปจากโรงแรมท่านไปเดินแล้วก็ท่านบอกเลยฉันมาเดิน9 โมงแล้วมันร้อนมากเลยที่ดีก็ต้องเป็นประมาณ6 โมงกว่าแล้วถ้าอีกวันท่านก็นั่นแหละคือเป็นคนสังเกตนั่นทุกอย่างเรามาสอนได้นะเพราะอันเนี้ยผมว่ามันเป็นตัวอย่างที่ดีของเรานะเราก็ถือว่าเป็นโชคดีที่ได้มาฟังท่านแล้วก็ทั้งได้สังเกตพฤติกรรมที่ของท่านเนี่ยนะคือตอนนี้จะดูว่ารางวัลโนเบล53 ล้านบาทเนี่ยนะท่านทำตัวนั่นปกติเลยเมื่อคืนดื่มไวน์ผมก็เลี้ยงไวน์ไทยท่านนะแล้วท่านชอบมากเป็นบอกผมไวน์ที่ทำในเมืองไทยเนี่ยมันไม่ชื่อสักเท่เลยชาโต้เดินเลยแต่ก็คือไวน์ที่ทำในเมืองไทยก็อันนี้ก็ถือว่าโชคดีของเรา Yes, Professor Blumberg and all the guests, I have elaborated somewhat and used with permission to use some of your very good example, to tell my students that to learn a lot because I tell them that as knowledgeable as you are, you still learn a lot. Last night you asked everyone about what we are doing, observe a lot of Thai ways. So I told my students, I relate to them that to learn not only from the content that you said, also from your behavior. Before the closing of today's event, I would like again to thank the International Peace Foundation, UA, the กสิกรไทยธนาคารกสิกรไทยคุณท่านรองประธานนะฮะท่านรองประธานของท่านธนาคารกสิกรแบงก์กสิกรไทยแบงก์ the Privy Councillor and the Chairman of the Advisory Board, General Surayut Juranun, all distinguished guests that come to our campus today, and especially Professor Baruch Blumberg. I hope that you continue to contribute your knowledge and research to mankind. We all of us here will always remember your speech and your behavior and what you have given us today. Please accept our appreciation, please. And I hope you travel safely back home and you have time you visit Thailand and our campus again. Thank you very much.
Thank you very much, President Narong. On behalf of Southeast Asia University, we thank you for your valuable time and participation, and we hope to receive your support again in the future. Thank you.